thought somebody else was chairing.
Can't find that person.
Received authorization. Next talk, I'm delighted to introduce Nicole Immorlica of Microsoft Research. She's going to be speaking on procrastination with variable present bias.
Thanks, and this is joint work with Nick Gravin, Brendan Lucier, and my student Manolis Puntarakis, who's on the job market this year. So I'd like to talk about situations in which agents make intertemporal trade-offs. So you have the opportunity to incur some sort of short-term cost in exchange for a long-term payoff. Some examples that I'll use in the course of this talk are you're a speaker in a workshop like this one, and it's the evening, and you can either prepare your talk or you can go to the movies. So you can incur a short-term cost, which is the effort of preparing your talk, or you can delay it and go to the movies instead. Similarly, if you're a student, you could study or party. If you're a marathoner, you could go on a training run, or you could sleep in the morning. If you're a skier, you could go through all the hassle of buying skis so that you have them for the rest of the season, or you could just rent when you go to the slopes this weekend. And in general, in all of these examples, you see a scenario in which an agent is making a sequence of costly decisions, and the costs and options on a particular day depend on the decisions they made in previous days. So I will represent this pictorially using what we call a task graph. There's a set of days. On day one is when the task has become something that you've determined that you want to complete. And on day n+1 is the deadline for the task. So for example, on day one, I've submitted my abstract. I've committed to what talk I'm going to give. And on day n+1 is I'm supposed to give the talk, so I better have it prepared by then. On any given day, you can have one of two states in this task graph example. So you could either have your talk undone or done. So let's imagine you just prepare it in one sitting. And the cost of preparing your talk, maybe it takes 2 units of effort, whereas the cost of letting it remain undone, there's some sort of mental anxiety associated with not having prepped your talk yet. So we'll say that it costs you 1 unit of effort. Now, clearly, if you're an agent facing this kind of task setup and you want to take the minimum cost path plan of action, you would plan on, well, I should write the talk on the very first day as soon as I submit the abstract. That's going to cost me 2, and that minimizes the cost that I have to pay to complete this task. On the other hand, we all know anecdotally that what we like to joke about is that we wait until the very last night and then we pull an all-nighter to prepare our talks. And that, as you'll notice, has a linearly higher cost than the minimum cost path in this example. But you know what really happens, although we don't like to admit it, is we are actually slightly responsible, and usually we'll wait a while and then we kind of get anxious, and in the middle of our period we decide, okay, I'm going to do the talk today. And so this is what the actual path often looks like. Economists have introduced, that model can't be explained through a rational agent's behavior, but economists have introduced what's called hyperbolic discounting to explain this type of performance in which we procrastinate for a while and then complete a task. And a special case of this hyperbolic discounting, which I'll focus on in this talk, is called present bias discounting, in which individuals inflate the present day costs by some bias parameter B, and when they evaluate the cost of any plan of action, they're going to calculate that cost to be B times the costs they incur today plus the future costs. So they're overweighting the present day costs. And you can see that this present bias discounting can account for the type of procrastination we saw in the anecdotally likely path of action for the talk prep example. So if your present bias factor is, say, greater than 2, then when you're on day 1, you're looking, well, if I prepare the talk today, I perceive that as having 4 units of effort because I've inflated my present day cost by 2. Whereas if I plan on doing it tomorrow, then I have this 2 units of effort, which are the mental anxiety of not having my talk done. And then I pay just 2 tomorrow, which is also 4. So if the bias is greater than 2, I'm going to end up planning on doing my talk tomorrow. But of course, when tomorrow comes around, I have that same exact calculation again. And I say, well, I'll just do it tomorrow again. And this continues until the very last day when your only choice is to prepare the talk. And so you prepare the talk. And so you can see that by having a present bias factor greater than 2, you take this anecdotally likely path. And it's linearly higher cost than the optimal path. For present bias less than 2, you're just going to prepare the talk immediately. And therefore, you get the optimal cost. But notice that for a generic bias factor, this present bias discounting only makes extreme predictions. And so in this paper, we introduce a tweak on the model, which we call variable present bias, in which the present bias factor of an agent is drawn from some IID distribution F at every point in time. So throughout this talk, I'm going to give you a bunch of examples to illustrate our results, and I'll be using this present bias factor distribution. So with probability 1/3, the agent wakes up, has a present bias factor of 1. So they're realistic about what's going on in their lives, and they understand all the the actual costs of any path of action. I'll call this that they wake up rational. With probability 2/3, you wake up and you're lazy. And so your present bias factor is something greater than 1, let's say 3. And as you can see immediately, having a present bias factor like this will allow for intermediate paths in the example of preparing a talk, because you're going to procrastinate until you wake up rational, and then you're going to prepare the talk. And so you're going to procrastinate for some constant number of days and then prepare the talk. So the question that I'd like to explore is, what is the impact of this procrastinating behavior on the costs that the agents incur while they try to complete some sort of task? We will quantify this using the procrastination ratio, which was introduced in a paper of Kleinberg and Oren in 2014, which is to say that the cost of procrastinating is the ratio of the expected weight of the path that the agent takes over the present bias distribution to the weight of the weight of the initial shortest path, so what the fully rational agent would have done. And the main result that I'm going to show in this talk are some bounds on this procrastination ratio that are a function of the structure of the task graph and the distribution of the present bias factor. All of the results are going to follow from a main lemma, which I will describe towards the end of the talk, which is that for any distribution, the worst case task graph has just 2 progress levels. So it's going to either remain in the undone, there's just 2 progress states. You either are done or undone. Your task is done, completed or not completed. And remaining uncompleted costs 0, remaining completed obviously costs 0, and there's a cost that grows with time to move from undone to done. So using that lemma, I'm able to derive some bounds on the procrastination ratio for certain cost structures on the task graph. Yeah?
So I understand that after you move along one edge, you don't resample, or you do?
You do resample. Every day you resample. So some days you wake up lazy, and some days you wake up, I don't know, active. Okay, and so I'm going to show some properties of the weights on the graph that are going to show that the procrastination ratio is at most linear, like it was in the leading example in the talk. And some other properties that, together with an assumption that you have a low enough tendency to procrastinate, that is that your bias factor is close enough to 1 often enough, then the procrastination ratio is at most constant. Okay, so there's a lot of related work, especially in the economics literature, on quasi-hyperbolic discounting, which is some generalization of present bias discounting. And in the CS literature, I've already mentioned the Kleinberg and Oren paper, where they look at having a fixed bias factor and study the procrastination ratio of various task graphs for a fixed bias factor. And there's this work kind of smells like this flavor of, can we introduce interventions or, say, structures on the graph that help people eliminate the costs? So there have been papers that look at choice reduction, like you commit today to not having options available in the future, which can help you circumvent the cost of procrastination, or delaying information. So there's this really cool paper by Jeff Ely about bings or pings or something. What's it called? Beeps? Where you're getting email, and when you get an email, your computer beeps, and that makes you go check your email. But you can have delayed beeps, and that can help you not waste a lot of time checking email. So it's a really cute paper. And then there's a recent paper that looks at how agents being sophisticated about their present bias can impact the procrastination ratio. So in the remaining 20 minutes, I'd like to tell you a model and statement of the results. And I'm going to spend most of my time describing my model and working through some examples to give you a flavor of the results. And then in the end, I'm going to spend maybe 5 minutes telling you about the main lemma and how we prove the main lemma. It has a really cute reduction, again, I had nothing to do with it, to optimal pricing. And so I think it's nice to see optimal auction theory showing up in other areas. Okay, so here's the model in general form. I have a task graph. I have some number of days. I need to complete the task on the n+1st day. The task graph consists of n+1 layers, being the progress states I can be at in any given day. In the ith layer, I have a set of progress states. And from each progress state, I can advance in the i+1st day to some other progress state. And the states I can advance to depend on the state I'm at today. So notice I might be able to gain progress or even lose progress. It might not be possible for me to stay at my same progress level. So this is a general task graph. The weight on an edge is the cost of going from that state u in day I to state v in day i+1. So the agent behavior is going to be modeled by this present bias discounting. So in each day, the agent is going to be at some node u, and they're going to draw a bias factor b from the distribution f, and then they're going to select a plan of action for that day and move to node v, such that that move minimizes their perceived cost of all their future actions, which is namely b times the present day cost plus the future costs. And we're going to define the procrastination ratio as the ratio between the expected weight of the traverse path and the weight of the initial shortest path. So this is the expectation over this bias factor b. Yes?
So the agents don't take into account their future procrastination?
No, they are naive about their future procrastinating behaviors. But the Kleinberg paper, Kleinberg et al. Paper addresses that in this past EC. Okay, so as I said, my main lemma, the workhorse lemma here, is that the worst case task graph for any distribution is going to have this form in which there's just the undone and done states, and the cost grows exponentially. So you can think about this as like a student trying to complete a homework assignment. The homework is assigned on the day of the lecture, and it's based on the material for the lecture. And every day they forget a little bit the material from the lecture, so the cost of completing the assignment gets more and more expensive. And so that would have this kind of structure. And so if we, for example, have a cost of 3 for completing the assignment on the first day, and it grows exponentially, with this bias factor that we've been working with, you can see that the expected cost of the student is going to be, well, if he completes the assignment on day I, which happens if he wakes up lazy on the first I-1 days and then is rational on the ith day, it's going to cost 3 to the I, and so you can see the expected cost is exponential, whereas the optimal cost was only 3 to do it on the day it was assigned. So a task graph satisfies bounded distance. This is the first condition I'm going to introduce to bound the cost of the procrastination ratio. It satisfies bounded distances if you can't ever lose progress. Okay, so think about this as a retirement savings account where you can always add money. The account is never going to dip negative, right? If you don't add money. So, so this student homework example was a non-example of that, right? Because from the first node, I had a path, the minimum cost path to the end was just 3, whereas from some other nodes, say this one, the minimum cost path to the end was 27. And what we can show is that if the task graph satisfies this bounded distances property, then the procrastination ratio is linear. And this is actually a quite trivial observation that you can all reason about. Why is it true? Well, on every day, your present day cost is, you're never going to choose to take an edge where the present day cost is more than the total path distance, which is bounded by the initial path distance. So every day you're incurring a cost that's at most the initial shortest path, and hence you get a linear bound. So I want to move on to the next example, which is showing that this linear bound is tight. And this is the training for a marathon example. So in this example, you decide on day 1 that you're going to run a marathon in 3 months, and you have no fitness level. You've never done anything in your life before, and so you're at level 1. And you can train and move to fitness level 2, or you can decide not to train, and then there's some epsilon cost, and you stay at level 1. Now, if you're ever at an intermediate level, you can just wake up and decide to train, in which case you increase your fitness level. But if you decide to sleep in, then you drop down. And you lose fitness by not training. And so that happens until you reach your peak fitness level, at which point you've decided that you love exercise so much that training is free, and so every day you can maintain your peak fitness level for free. And finally, on the day of the marathon, if you are at your peak fitness level, it's free to run the marathon, but for any other level, it's costly because it's very painful when you're not fit enough. So for this example, the minimum cost training plan is to train every day until you get to your peak fitness level and then go run the marathon. But if you think about the perceived cost of the options, so for an agent with a bias drawn from our favorite distribution here, if the bias was 3 on some morning, then it's going to be cheaper for that agent, and you can do the calculation, to sleep in. And so they're going to sleep in, and as you can infer by now probably, this looks like a bias random walk with some downward drift. And therefore, and an absorbing state at M. And therefore, if M, your peak fitness level, is high enough, you're going to sort of wiggle around in the intermediate levels until the day of the marathon, and hence spend about N, and opt spends just log N. And this example can be improved to give tight bound to the bounded distance theorem. Okay, so I want to improve upon this. I want to get an even better procrastination ratio with more assumptions on the problem setting. And so I can, what was sort of wrong with that was that you lost progress in the marathon training example. If you slept in, you were losing progress, and that was what was really hurting you. So I'm going to introduce another property, which we call the monotone distance property, which says that every day you don't lose progress. Your distance to your goal tomorrow is at most what it was today. And so the marathon example, of course, doesn't satisfy this because your distance to the goal, if you don't train, increases. And what we are able to show is that if your task graph satisfies monotone distances and you're sufficiently rational, so I'm not going to precisely define what equation we have for this, but there's some condition you can place on the distribution, which means that it places sufficient mass near 1. Then the procrastination ratio is constant, and this constant will depend on the parameterization of your present bias distribution. A sufficient condition, for example, is our favorite distribution in which you have constant point mass at 1. So for example, here we imagine renting skis or buying skis. So buying skis is annoying because you have to do some research to figure out what skis to buy. So that has a cost of 1, whereas renting skis has a cost of, say, 2/3 because you have to go rent the skis from the rental place. And so the present bias factor 3 is just going to rent all the time, whereas the oh, and notice this satisfies the monotone distances. You're never losing your progress. And so the guy that has a constant probability of being rational is going to have a constant procrastination ratio. So those are the set of results, yeah?
So if you have a constant probability to be 1, then after, let's say, p, then after 1/p days, you become rational, and then you will take the...
Yeah, so this relies on that main lemma that I am going to discuss next, which is that the worst case task graph looks something like this. Otherwise, I mean, that sort of argument is saying that when you wake up rational, you can make all the progress you need. And so I need to argue that the worst case task graph looks like this, and then the theorem follows rather trivially. Our parameterization of the distribution F allows us to see how it sort of degrades as this condition holds less stringently. So let me talk a little bit about that lemma, which has a really neat connection to optimal pricing. So just to remind you, I'm going to show you that for any distribution, the worst case task graph looks something like this. Notice this doesn't actually satisfy monotone distances. So for that previous theorem, I'm going to need to reprove this sort of worst case task graph, but it's going to use the same machinery. So I'm just going to prove it for the graph with no conditions. So how am I going to construct this worst case task graph? I'm going to do it iteratively at every day I. I'm going to, and for every progress state in layer I, I'm going to construct the progress states in layer I plus 1 and the weights for the transitions from layer I to layer I plus 1. And I want to do this in a way that maximizes the worst case procrastination ratio. Notice without loss of generality, I can assume that the distance from S to T is 1. I just can normalize everything by that. And so I'm going to also inherit in this iterative construction some constraint that I must satisfy on the shortest path from today to that goal. So on the very first step, I'm going to start at day 1, which has only one progress state by definition, S. I'm going to construct the potential progress states on day 2, and I'm going to have to choose weights such that there is some path from day 1 to the end that had distance 1. And the idea is to draw an analogy to the single agent pricing problem. So I don't have time to go through the analogy very precisely, but I want to give you some sense, some flavor of how this works and why these problems are related. So in the pricing problem, as Shuchi very nicely described, we have a single item that we're trying to sell to an agent, say in the single shot setting, so I'm not worried about dynamic mechanism design here. And the agent has a value drawn from a distribution. The auctioneer can set up some prices. So a menu of prices. This would be like, I'm going to give you the item with probability x1 if you pay me p1. Give you the item with probability x2 if you pay me p2. And then the buyer is going to pick an option from this menu. Say, OK, I want the item with probability 3/4, and I'm willing to pay you $2. That's the thing that maximizes my utility, which is v times the probability I get the item minus the price I've paid. So that's the pricing problem. And it has a very similar structure to the planning problem. The buyer is equivalent to the agent in the planning problem. The present bias parameter is like the value. The choices of where to go next, the plan of action today, is like choosing an item from a menu. Now, there's one sort of thing that's a bit difficult, which is that the objective of the procrastinating agent is to minimize some perceived cost, whereas the objective of the buyer in the single agent pricing problem is to maximize some utility. But a simple transformation of this objective, preserving the optimal solution, we can transform it into a maximization objective, which will end up having this form. I think I just multiplied by maybe this or something. So once you get to this form, you can see that these two objective functions also look very similar. The value of the agent is the bias parameter. The probability of allocation is the fraction of distance you cover today. And the price is the fraction of distance that remains tomorrow. So with that analogy, the other thing is what's the objective of the iterative construction. Our objective is to set up this menu, or these choices here, in a way that maximizes the incurred cost of the agent, or maximizes the procrastination ratio. We're trying to construct the worst case task graph. And the incurred cost is going to be some linear function of the weight and the distance parameters. And now we can invoke optimal pricing theory. So Meyerson showed that to maximize revenue, there's a menu that you can pick which has just two options. One is don't receive the item and pay nothing, or receive the item for sure and pay P. This theorem, I actually wasn't able to find a statement of this, but you can check that it's pretty easy to generalize from maximizing revenue, which is just the sum of the p's, to any objective function that's linear in the p's and the x's. And then the same statement holds. So you can have just two menu items that are going to maximize your objective. And so we can apply this to our setting, in which what we now can see is that the worst case, when we're trying to figure out what the continuation of the graph should look like from node U, we only need to have two menu options. One should correspond to the individually rational menu option. One should correspond to the menu option where the agent buys the item. And that's going to, once you look at this analogy here, it's going to result in having some weight here and 0 here, 0 here, and p times the distance here. So sort of piecing that all together, and there's some stitching that you have to do, so it's not necessarily trivial that you can stitch them together, but because of the structure of the weights we've calculated, you can stitch them together and you get a graph that looks like this. So in summary, I've defined a special case of hyperbolic discounting with variable present bias. And that lets us study agents that procrastinate, but perhaps not indefinitely. And then we looked at conditions that will guarantee that the procrastination doesn't hurt the agent too much, including bounded distance, which is like you never dig yourself into a hole, so you can't withdraw more money from your retirement account than is in there in the first place, or monotone distance. You always make progress towards climbing out of the hole, which is like you're forced to put some money into your 401k by your employer, or, and that works if you have a low tendency to procrastinate. So thank you. Yes?
So I'm wondering, the assumption that the bias is IID in each round, that seems, if I think about the motivating example with the anxiety, like the anxiety increases and for many people the bias then decreases, but is that just captured by edge weights? Like could you
Yeah, so the anxiety I'm using as an edge weight. It is an edge weight in my example. So I guess one question you could ask here is like, what if the edge weights were drawn from a distribution instead of the bias factor? So you have a fixed bias factor, but the edge weights are drawn from a distribution. And then I guess if the distribution is set up correctly, our results will apply, but it would need some sort of independence, which is maybe what you're objecting to. Yeah?
If that helps, I am IID most of the time. So.
Kira?
I was just wondering if there's been any work. This is on like traversing a graph that has cost, but instead on like a setting where you have a buyers have a value with some bias, and you're trying to design mechanisms that maximize revenue.
Yeah, no, that's a very interesting case. So the Kleinberg-Oren paper was, I think they, at least the talk about a setting in which the goal has some value to you, and you can try to traverse the graph and look at ways to maybe remove edges to make it more likely that you reach your goal. So the example they like to give is, you tell your child that like they could be Beethoven, and that encourages them to practice piano, which helps them reach the goal of being proficient at piano, which has a lifelong value, even though they never really were able to reach the status of Beethoven. Yeah?
So what's the intuition in the worst case task graph? The prices of the second menu are growing exponentially.
So that comes from the structure of when you apply the Meyerson lemma. You're multiplying the remaining distance by a factor p.
So I have a different view of why people may not do stuff, because the task may just go away.
So there's some chance if you don't reply to the email, the student will stop.
Right. You get back the same result if you assume that it's a probability it just dies.
Don't run the marathon.
Right.
The workshop will be cancelled.
That's interesting. I haven't thought about that. I would like to maybe resolve that by changing the cost on the final layer. I could have an extra day before the last day in which...
Every day the thing might die, right? So you don't have to do it.
Yeah, but I want to add another progress level, which is done, which I can transition to. I guess then you want to transition there probabilistically. Yeah, I don't know. I'd have to think about it.
I think it's especially interesting when you provide incentives, right? Because then, the incentive it's like administrative work at a university. It's actually the incentives are actually to wait and maybe.
Yeah. Do you want to stop?
I see there are other questions in the room, but I want to give Matt time to speak before lunch. So let's thank Nicole again.